Okay, I'm going to create this video and I'm going to try to walk you through all of the Six Flags labs in about 10 minutes. Now, you're going to have to slow them down in order to get the answers, because I'm not going to spend a whole lot of time in the answers. I've got these answers already pre-done for you. So you just pause the video when you need to copy stuff down or whatever, and get these things turned in. Alright, here we go. Alright, so you should tell me why you think we should go to Six Flags. This is important. What would you tell an administrator? And then tell me the 3 best things about Six Flags. If you didn't go to Six Flags, you know what Six Flags does. So use your imagination. And then how could the teachers improve it? This is from the teacher's perspective. Maybe things like, I don't know, just something. Maybe help you out on labs like I am. How could Fiesta Texas improve it? I'm thinking lower the prices, extend the hours, sell fast passes, things like that. And then how could the high school and buses. Next year we do charter buses. So, right. So these may not be in order, the order you have them. They are, then awesome. If not, go to it. So there's a video on each and every one of these rides. They are right here on this YouTube channel as well, and you can watch those to get any kind of timing you need. So here we go. Alright, first thing I want you to do is draw free body diagrams. These are the boxes with the arrows. So you're going to draw the free body diagram. You're going to, when you're sitting still, you have gravity pulling you down, the normal force holding you up. When you're going up, again, gravity's pulling you down, normal force holding you up, an applied force from the engine going up that way, and then air resistance is always opposite of the applied force. And then when you're going back down, again, gravity pulling you down, normal holding you up. This time the applied force is in the opposite direction, and air is opposing the applied force. It asks you to sketch a time versus position graph. So the ride starts at the 0 position here, it goes up to the maximum position, returns back down to the 0 position, and then it does it again for the other side, and then again, and again, and again, and again. And so that's what your time versus position graph will look like. Alright, calculate the period of the boat. Show the formula and show your calculation. So period equals 1 over frequency, or it's the time it takes to complete one cycle. So it's the time it takes to complete one cycle. One cycle for the boat would be, the boat goes up, and then, so you start the cycle here, you go stopwatch start, bam, and then there, and then turned around and comes back, and that's one complete cycle. And I timed this 3 times, and I got 7.5 seconds. You're welcome when you watch the video to time it and get your own time. That's flexible, but you should have somewhere in the neighborhood of that. And what are, or were, the small pops of airtime that's alluded to in the description? That was when you were out of your seats, and that out of seat time is considered what they call negative g-force. Okay, moving on to the next question. Okay, the boat becomes disconnected from the pendulum at 20 feet in the air, and then assuming that you're traveling at 14 meters per second, how far will the boat travel? Well, the first thing we would have to do is convert feet to meters. So there's 3.3 meters in each foot, so you take 20 feet divided by 3.3, and you get a distance in meters. And then we apply the distance to the time formula. So we're looking for the time that you would actually be traveling, because what you're creating here is you swung up with the boat here. Okay, so you're swinging up. So here's your boat. You're up to the top here. You're on your boat, and then the boat becomes disconnected, and it goes. And then at some point, the boat's going to hit the ground. And so what we want to know is you create a projectile, and we want to know how long is it going to take before it hits the ground. And then we'll take that time and we'll multiply it times the speed that it's traveling, and that's going to give us our horizontal distance away from the launch location. And when we do this math right here, using acceleration due to gravity of 9.81, so it's, the formula is the square root of 2 times the distance, which we just converted from feet, divided by the acceleration due to gravity, you get 1.11 seconds. So that's how long it will be traveling at this speed. So if you take 14 times your 1.11 second, that's going to give you your distance away from its launch point. And I'll let you do that math. Alright, moving on to the next one. The bus ride. So this is a mandatory lap, whichever of the labs you choose, this one you must do. So here are the directions. The first step tells you to develop a scale, so the vector map will fit onto a graph paper. Alright, so you're going to put together a scale so that you can use graph paper to graph the vectors. And so the first thing you do here is develop a scale. I used 1 centimeter is equal to 5 miles. That's what I chose to use. You can use whatever scale you want, but that's what I chose to use. And then all you got to do is you take your miles and you divide them by whatever you chose. In my case it was 5, and that converts it from miles to centimeters. So this is going to give you your magnitude in centimeters that you're going to draw on your graph paper. And so you're going to have a little piece of graph paper, like so. You'll draw your little boxes on it. Right, so you're going to have your boxes on your graph paper. And then you're going to just use a ruler and you're going to measure it. Here are your angles, so you're going to use a ruler or protractor. And then you're going to draw each of these vectors, or whatever they are, mapping it out. And so here's what MapQuest did, and yours should look similar to that if you set up the directions and everything correctly. And you'll turn that in with your lab. Alright, moving on to the next one. Okay, what is a vector? What is a scalar? So here are your answers. Vectors measure magnitude and direction. That's why we did magnitude and direction. And examples would be displacement, velocity. Scalars measure just direction, or just magnitude only, distance and speed. Okay, so the first one asks you for total distance. Again, that is a scalar quantity. So we don't need direction. We just need to add up all of these miles right here. Add those all up, hit the total button on your calculator, and you get 107.25 miles. That's the one-way trip. Multiply that times 2, gives you the two-way trip, 214.4. Displacement, however, since that's magnitude and direction, and since our round-trip displacement started us here, we went all the way this way, and then turned around and went all the way back this way. We ended at the same spot we started at, so our displacement is 0. Okay, next question. Estimate average speed of the round trip. So there's our 214. This is going to be distance divided by time. 214.5 divided by, I averaged our time at 4 hours. Gives us 53.6. If we do one-way distance, it's the same thing, only we just use our one-way distance and one-way time, and we end up with the same average there, using the same formula here. You must have these formulas, otherwise you don't get credit. Alright, how far is San Marcos from Pflugerville? If it takes you 1 hour and 22 minutes and you go at 53 miles an hour. So that's just going to be the distance formula is going to be velocity times time. It's how fast are you moving and how long do you move at that speed. So first thing you got to make sure is this is 22 minutes. So that's going to be 22 divided by 60 to give you the amount of time. And that's actually been like 1.33 or so, 1.38 I think it is. So that's how many hours that you're traveling, and you're traveling at 53.1 miles per hour. And so if you do that math, you'll get the distance away from Austin or Pflugerville, San Marcos is. And then if you had a helicopter that moved 10 times faster than the bus, how long would it take you? Well, then you just take the average bus speed, multiply times 10, that gives you the helicopter speed. Then you would go ahead and take your miles divided by your helicopter speed, and that's going to give you 0.2 hours. So the helicopter is much, much faster. 0.2 hours. Okay, next question. Here we go, we're moving on to the Superman. Again, watch the video. Alright, these questions simply ask you to label the point of the highest potential, or the most potential energy. That's going to be the highest spot. Potential energy has to do with height. So I labeled that as the highest spot, which I thought was at the top of the first hill. The most potential energy is also going to have the least kinetic energy. So I also labeled F here. Those two should be in the same spot. And then the most kinetic energy will be where there's the least potential energy. And that I labeled here because I thought that was the lowest spot, so it's the lowest spot. And then it asks the second highest or the second most kinetic. There's potential up there and kinetic here. Alright, and so it's going to be labeling that like that. Next one asks you for calculate your own personal gravitational potential energy. So this is for you. So that's why you're going to use your weight. You're going to need to convert your weight into mass first by taking your weight in pounds, dividing it by 2.2, and then that's going to give you your mass. So the answer to this is going to go right in here into this formula, where you will then multiply it times gravity, because there's the g. So this is your mass times gravity times the height, which I went ahead and gave you as 51 meters, which came from the information sheet on the front page. Alright, and then it says to calculate your kinetic energy. Again, you're going to use your mass, so you use the same mass you got here. It's going to go down there. And the formula for this is 1/2 times your mass times the velocity of the ride squared. The velocity of the ride is 70 miles per hour. You can't use miles because your mass is not in miles, and the distance, the height is not going to be in miles. So we have to use meters, and of course the kinetic energy needs meters. So we're going to convert miles into meters by multiplying it by 1601 and then dividing it by 3600 to go into seconds and hours. And so we end up with a velocity of 31.3 meters per second, and that's what's going to go in here. And we're going to square that number, so don't forget to square that. So it's going to be 1/2 times your mass times 31.3 squared. Don't forget to hit the square button or you'll go with the wrong answer. And then that answer will go in there, and that'll take care of that one for you. Alright, now this one says that how much energy was lost. Well, you would take your answer from 2, because that's the kinetic energy, your answer from 3, because that is your potential energy, or vice versa, I should say. That's your potential and this is your kinetic. So this is going to be your PE, and this is your KE. Subtract those, and that's going to give you the amount that is lost. And where is that energy lost? It is lost in the conversion to heat, so that's from friction, and the conversion to noise due to friction. They're both due to friction between the tracks and the wheels of the coaster. But it's heat and noise. Alright, moving on to the next one. Alright, so the Superman uses a clothoid loop instead of a circular loop. These are diagrams of the clothoid. Notice that this does not have a uniformed radius. This radius is much smaller than the radius top to bottom, whereas a circular loop has a uniform radius. The advantage here is the circular loop requires a greater amount of speed, somewhere in the neighborhood of 200 miles per hour for a circular loop to complete the loop, whereas the clothoid only required 70 miles an hour. So you can see that if you try to go 200 miles an hour on a roller coaster, the car would never stay on the track. We'd all die. So this is important for them to use this kind of loop to keep us alive and keep us safe. Okay, now the Iron Rattler. Again, watch the video. Moving on to the questions. Acceleration due to gravity, that's constant. We've given that to you a million times in physics. It's right there, 9.8 meters per second squared. And then it says, using the approximate data and the equation for MP is mass times gravity times height, potential energy. Find the potential energy at the top of the Rattler. That's the same exact thing that we've done before. It's going to be your mass times your height, or times gravity times the height, which I've converted in meters already for you. So this is the same thing we did for Superman. Okay, and then it says according to, let's do the velocity this time. So we're going to just do a manipulation of this formula. So we started with this formula, which is 1/2 times the mass times velocity squared, and we manipulated, and we came up with this formula there. These are our numbers that we plug in. So that is our 2, that is our KE that we just calculated. This is your mass again, and then you plug those numbers in, hit your enter button, and that should give you the velocity of this ride. You're going to skip 4 entirely, so do not have to do 4. Don't worry about that one. 5 explains in terms of force how the Rattler increased the intensity to ride. So they made the hills bigger, which gives you more gravitational potential energy, more force going down the hills. They made them steeper, again giving you more force. More G-force means more thrilling, exciting ride. Okay, free body diagrams. Again, we're interested in and I made these carts. You don't have to be as fancy as me on the draw. You can just use boxes. But what I do want you to notice is as you're going up the hill, you've got the force of gravity which is always perpendicular to the ground, but the normal force is perpendicular to the angle of the hill. So that's how you should draw those. When you're at the top of the hill, your angle of the hill and ground are the same. So this just looks like a regular free body diagram. And then when you're going down the hill, again, gravity is perpendicular to the ground. Normal force is perpendicular to the angle of the hill, or the angle of the cart, which is one you want to use there. Okay, now we'll do the twister. Again, watch the video, very important, watch the video. Watch the video, watch the video. Alright, number 1 I'm going to allow you to skip, so skip number 1 on the twister. Number 2, calculate the work done to lift the maximum number of passengers, ignoring the weight of the ride, and show your formula. So the number of passengers is 40 on this ride. The height that they need to lift them to is 75 feet. So 75 feet is the top, and 39 feet is where they start at the bottom, and so the actual lift is 36 feet, or 11 meters. So that's how tall they got to go. And work is a product of force times distance. Force is a product of mass times acceleration. Here's the acceleration due to gravity. So we're going to take the mass of the guest, in this case, and to calculate the force. So the mass of the guest, again, we'll use your mass, whatever your mass is, and then times that by 40. So for me, it would be 75 times 40, and I would do that, and that would be, so I'd have 3,000 kilograms. And then times that by 9.81. And just for simple math, I'm going to do times 10, so that would be 30,000 newtons of force, and that's times the distance of 11 meters. So that means the work done is approximately 330,000 joules of work. Lots of work to lift all those heavy passengers. Okay, moving on to the next one. If the twister is operating at a maximum horsepower of 240,000 kilowatts, how long will it take it to lift it? So you just take that work that you just did before. You're solving for how long, so you're going to take the work that you did before. You take the power is going to be divided by the work to give you the time. So there you go. That should take care of that for you. Calculate the work done to lower it. That's going to be the same since you're using the same numbers, but it will be a negative because it's going down, and vector convention says it's going down, so it'll be the negative number that you got here, the negative value of that number. And then it says why. Why is it negative? Because the acceleration is negative, because you're going down, so you would end up with a negative force, and that would be a negative work. Okay, and does it require more work to lift the riders up? Does it require more work to lift the riders if the ride is spinning? And the answer is yes, because the formula used for work. However, the acceleration you have due to gravity plus an additional acceleration, which is due to centrifugal acceleration or the circular acceleration. So that means your total acceleration is going to be more than 9.81 meters per second squared. We don't know exactly what that is. We're not making you calculate that, but it will be more. And then finally, describe the centrifugal force. So the circular force is the ride spinning. And then it says, why is centrifugal force on people who dare to ride the ride greater than a ride like SS Overboard, which has regular swing, because this ride is going to be swinging and rocking at the same time. So you have two separate forces that are being applied to you, so you get more force. Alright, finally, let's talk about the scream. Again, watch the video. Important to watch the video. Here we go. Describe the sensation between the scream and you as the ride catapults you up. It makes you feel heavier, like you're in a rocket ship. When it's catapulting you down, it makes you feel lighter, like you're in free fall. So, heavier on the way up, lighter on the way down, same as when you ride an elevator. How long did it take? Well, if you time it, watch the video and time it. Get your own time here. I got 2 seconds. And then it says calculate your average velocity on the way up, and is it positive or negative? So your average velocity, you just have to calculate, you just have to multiply the distance of the ride times the time that it took you, and the distance can be gotten right here. So the distance is approximately 20 stories. So 20 stories at about 4 meters per story. So if we took 4 meters per story, so 4 times 20 is going to give you about 80 meters. You take that distance divided by the time it took you to get there, and so that means you're going like 40 meters per second for that. And then here we go on this last one here. To come back down, it took you 3 seconds. So here we go, and we're just do the same thing. We're going to use 80 meters divided by 3 this time, and so that's going to give you, what is that? Let's do the math real quick here. 80 divided by 3 is 26.6 continuously, and again that's meters per second, so it's a little faster on the way up than it was on the way down. And then finally, did the scream and you ever achieve free fall? Defend your answer. The answer is no, 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 because you have air resistance. There's friction between you and the ride, and the ride has brakes, so there's at least 3 good defenses. And remember, free fall is in the presence of no air resistance. If you were to do free fall, how fast would you be going? So you'd take the time divided by the acceleration due to gravity, and that gives you the speed that you would be falling if you were free fall. And you weren't going that fast. 130 is going pretty fast, but not quite. And then finally, let's draw our 2 free body diagrams between you and a coin sitting on your hand. So you would have gravity pulling you down, normal force pulling you up. The coin would also have gravity pulling you down, and normal force pulling you up. Since those are basically the same forces, the coin would stay in your hand. So this would stay in your hand, stay in your hand. And then the very last thing you could do is, if none of these slabs appeal to you, you could create your own lab. And if you do that, you need to make sure that you have measurements, you have at least 6 questions, and you include at least 2 vectors. Alright, this should be plenty of help for all of you to finish this lab. So at this point, it's already late. Let's get it turned in immediately. Thank you. Have a great day.